and please कोई like इसको touch मत करना. Please proceed.
अभी गुड टू गो.
Yes,
सो मैं स्टार्ट करूँ. शुड आई स्टार्ट.
yes, yes, it's working.
ओके. सो आई स्टार्ट लाइक. ठीक है. 3, 2, 1. Okay. So, hi everyone. So today we are here to present our final presentation on the topic 3, which is the nonlinear optic at an interface. So let's start with a brief introduction about the topic. So what we all know is nonlinear optics is the study of the interaction of the light with the matter at high intensities. So one important nonlinear optical effect is a second harmonic generation. So in second harmonic generation, we know that two photons of the same frequency are combined to generate a single photon at the twice of the frequency. So in this context, so what happens at the interaction at the surface is that when the light is incident on a surface between two different or two dissimilar optical materials, see, like we have here linear and nonlinear. So a second harmonic wave can be generated at the interface, and this is because of the presence of the so this is because the presence of the interface, which is here, it breaks the inversion symmetry of the material, so which is required for the material to have in order to have a non-zero second order nonlinear optical susceptibility. So you can see here. So let's figure out what is happening in these images here. So in case A, you can see that the incident light, which is this omega I, so its fundamental frequency is omega I, and it is what happens is when it is so it is partially reflected and it is partially transmitted into the nonlinear material here, which is this part. So the transmitted light, it creates a nonlinear polarization of the frequency omega s, as we can see. So omega s is actually twice of omega I within the medium. So this nonlinear polarization gives rise to radiation at the second harmonic frequency, which is then reflected out of the material. So now we can see in case B, what happens is the light is again, it is so the incident light is also again partially reflected and partially transmitted into the nonlinear optical material. But however, the case here is that since the material is centrosymmetric, so the nonlinear polarization at frequency omega s, which is basically twice of the omega initial, it must be generated into a very thin layer near the surface. So this is because the presence of the interface, what happens is that it breaks the inversion symmetry of the material, and once it breaks the inversion symmetry, the second harmonic wave basically is generated in this thin layer, and then it is emitted into the surrounding space. So now let us look at the equations of these waves. So if you can see here that this is our initial wave, initial incident wave equation here, and then we have about the transmitted wave. And next, we can see here this equation here. This basically describes the polarization, nonlinear polarization, basically, which is generated in the nonlinear optical material with its frequency omega s, as you can see here. And one thing that we can realize is the amplitude p here, which is the uh, sm- small case p. So this p is basically proportional to the square of the amplitude of the transmitted fundamental wave, and it is also proportional to the chi2 tensor here, which is basically the measure of the nonlinear optical susceptibility of the material. And then we have this equation here, which is ks, which is basically the wave vector of the second harmonic, and you can see that it is twice the wave vector of the transmitted fundamental wave. And then you can see that again, this is basically the wave polarization unit vector. So, please note that here we are considering that the case of polarization P is perpendicular to the plane of incidence. So now, if we consider the nonlinear polarization radiation, so you can see that the equation, so basically, so the non-linear polarization give rise to this reflected wave of the omegas, and it is we can write the equation in this form. Now we can so in order to calculate the solution for this equation, so first we'll calculate the homogeneous solution for it. So the respective homogeneous equation would be written like this, as we are considering the right hand side to be zero, and this is how we are getting its solution. And then we'll calculate the a particular solution, which is then further calculated and concluded to with this. So now if we take these two solution and we substitute it into the initial equation, so we'll get this solution somewhat like this, with the considerate v vector of the transmitted and the reflected wave here. And next, yeah, so this is done from my part.
Hello, I am Mukesh. Now I'm going to speak about the next part. Wait a minute. Uh, Hello, I'm Mukesh. Uh, Now I'm going to continue the next part. So here above we have written the nonlinear wave equation due to the polarization. This is the equation, and now I'm going to say like how we are going to derive this equation from the Maxwell equations. So let me start with the Maxwell equations. These are the four Maxwell equations, and now we are going to consider the case where uh, there are no free charges and there are no free currents. So rho and your j vector are 0. And now take your uh, third equation where del cross E equal to minus rho b bar by dot t. And here you take the color on the both sides, and on the right sides you get minus del cross rho by dot t of b vector. And now you can interchange between the del operator and the dot by dot t operator, and you get dot by dot t of del cross b. And instead of b, you can write it as b as mu naught in h for the non-magnetic materials, and you substitute del cross h as in that equation, and you finally arrive at this equation. And you can write the d vector as epsilon naught times e vector plus p vector, the polarization vector. And you can write this for the nonlinear materials. And now uh, we substitute the value of d here and we get this equation. And now this p vector can be written as p linear vector plus p nonlinear vector. And the d vector can be written as epsilon naught e vector plus p linear vector plus p nonlinear vector. And your epsilon e vector plus p linear vector is d linear vector. So now we substitute that instead of e. Uh, Actually, here is one more step to do. While simplifying this part, there will be two terms. One is minus del square e, this the one, and the other thing is del dot t. Here in this case, I mean, we like to take the I mean, not the e part. Sorry. Uh, Substitute the value of e by using this equation, and this will get a part of del dot d, and we are considering del dot d as 0 here in this case, and we are keeping del square d as normally, and instead of d again we substitute the e part, and finally you get this equation while writing epsilon d plus b linear as b linear. And now for the lossless and dispersionless media, you can dash the linear as epsilon into this uh, dialectic constant, linear dialectic constant into a t vector. Here we are considering the case where your dialectic linear constant, dialectic constant as a scalar, and we know that for dispersive medium, you can write the E vector as sigma of n of E of En of R of t into e power minus I omega nt for different frequencies. And you substitute that equation with the above equations, finally arrive this equation. And this is my part.
Hi, I am Praveen, and I'm continuing after my partner, and I'm going to discuss about the boundary conditions. For boundary conditions required for that the components of E and S tangential to the plane of interface, and that should be continuous. And from these conditions, that should be satisfied. There is a criteria for that. There must be existence of second harmonic reflected wave that is required, and the equation for that is ER in omega s is equal to AR in omega s into e to the power KR in omega s into R. That is equation third, and for the boundary condition that should be satisfied, and for each point there is an interface, and that is the wave vectors, and the wave vectors are Ks, Kt in omega s and Kr in omega s, and that should be identical components along the interface. And the equation for that is like ks in x is equal to kr in x in omega x, and kt in x in omega s, and that is the fourth equation. After doing all these things, we are going to simplify, and after simplification, that is ks equal to 2kt in omega I, and the magnitude of the vector that can be expressed in the terms of dielectric constant are the three equations. There are three equations. The first equation is kt omega s equal to epsilon t to the power half in omega s into omega s upon c. Similarly, the second equation will be the kr in omega s is equal to epsilon to the power half in omega s into omega s upon c. And the third equation is ki in omega I is equal to epsilon r to the power half in omega I into omega I upon c. And similarly, we can also write the ks in terms of dubious dielectric constant epsilon s, and the equation for that will be uh, ks is equal to epsilon to the power half into omega s upon c. So in boundary conditions, there are four conditions. I mean, not the four conditions. There are four terms we can use. The first condition is like there should be E and H that is tangential to the plane of interface, and that is also that should be also be continuous. And after this also should be satisfied that the existence of second harmonic reflected wave, and there is equation for that, that is ER omega s in AR in omega s into e to the power K R omega s dot R. And this should also be satisfied by the interface the vector waves, that is Ks Kt in omega s and Kr in omega s, and that should have the identical component along the interface. And we have already gone through, and after this the equation was ks is equal to 2kt in omega I, and we have also discussed the wave vectors, the magnitude of wave vectors that are expressed in the terms of dielectric constant. There are three equations that are already discussed. In the last, we can easily write down the ks in terms of previous dielectric constant epsilon s, that the equation will be ks is equal to epsilon to the power half into omega s upon c. And I am submitting this. I have done this, and thank you.
Right. So yeah, my name is Earth, and I'll be showing you the Null's law and the continuity. The Fresnel's equation. I mean, well, before we proceed, I'd just like to say that board actually had a lot of typos, uh, and that was very painful to understand. If you ever wish to study, it's better to just take look at the reference given in the board. Anyways, moving on, we've got this pictures dielectric constant, right? And we've written these wave vectors in terms of their dielectric constants, right? What we're doing is we can right our Snell's law, sine theta upon theta, that's mu, right? But mu can be written as c naught by c, which itself can be written as under root, mu epsilon naught of mu epsilon upon epsilon naught mu naught. So you see, epsilon to the power half, that's proportional to sine theta, right? So what we're doing here, I mean, as you can, if you take a look at this diagram, we are equating the x components here. We've done that over here, right? And we're looking at the corresponding sine thetas, right? We get these equations, kt of omega s, 2 omega sine theta t, that should be proportional to epsilon naught t to the power half uh, times sine theta t. And there's also a factor of omega s by c. Similarly for the reflected wave. Uh, and so if you were to compare the dielectric constants and the sine theta, you get this equation, which is important, right? This is a generalized Snell's law for nonlinear in nonlinear optics, right? All right, so Fresnel's equation, right? I'll be completely honest. I have not completely understood how the Fresnel equations behave in chi2 effects, but the linear part, but the linear regime, that's simple enough to understand, right? This wave coming in the xz plane, bounces off the z equal to 0. That's our plane of reflection, right? So if you were to simply like equate ER plus ER equal to ET, again, please note that we are looking at polarization perpendicular to the plane of incidence, and the Maxwell's law, we must have E perpendicular to the plane and H in the plane, and yeah, with our usual right hand rule. Right, we look at ER plus ER equal to ET, and we equate, like cos theta of B by mu. That's our H. And we also write B in terms of E. Right? With these three equations, we can readily show the reflection and transmission coefficient, right? There's this over there, right? These are the Fresnel's equation for the linear thingy, right? Right. Well, basically, we have to ensure that the electric field and the H field, they are continuous while going from one media to another, right? And we end up with these relationship between the transmitted and the reflected amplitudes, right? You can see that these are, like, if you treat AT and AR as variables, we get this as two equations and two variables. With our Cramer's rule, we get AT and AR in terms of the other coefficients, and right, this is what we get, proportional to dielectrics multiplied by their respective cos thetas. This times T perpendicular upon epsilon naught s minus epsilon naught T of omega s, right? we get AR and AT. Now we plug them back in the equation of our electric field, right? What is that? This is ER, this is ET, right? We plug them back in, and yeah, with some algebra, we get ER as that. And so this is a big, intimidating looking equation. But this is basically, I mean, the P perpendicular upon the denominator. That's just the amplitude. I multiplied that by the e to the power I k r dot r, right? Uh, right. Also, please note that these in the denominator, apart from the epsilon naught r, you see cos thetas are of the order 1, and uh, uh, epsilon naught t. Just a second. It comes up later. Right, AR is of the order of magnitude p perpendicular upon 4 epsilon naught epsilon. So you can see that this boils down to basically 4 epsilon naught. I mean, we have 2 times 2. That's how 4 comes up, and each of them is of the order of epsilon naught. Right. Again, as shown above, that the x component of the second harmonic and the transmitted uh, wave as well as the reflected wave, they have the same x components. And so if you were to subtract ks and kt, you get a vector along the z-axis. Right, that's our delta kz. Now, we put that in the equation of ET, the transmitted electric field, right? And we take out this part. We take out the e to the power I kt of omega s dot r, right? With some algebraic magic, we end up with the equation of the electric field, transmitted electric field. And now, what happens if that there's an imperfect phase matching? If delta k is much lesser than 1, so Divyash takes care of that. And yeah, if you guys will meet on second. Thank you.
Uh, so hi guys, I'm Divyash. So far has explained by Earth. So I'm thanking him and I'm starting my part. So there is very interesting progress here, uh, which is related to approximations and the end results. So here we are approximating delta kz is less than 1. There are few main reasons. Basically, first one is uh, the amplitude spatially varying due to very imperfect phase matching. And second reason is we can see in the graph that the 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 physics, the area in which the physics happening, the thickness is very less. Only at the surface the second wave is generating, which is the order of uh, the order we will find, but it is very less. And beyond that thickness, beyond that imperfection, the wave 2 omega wave is not existing. So due to that, we are taking approximation of delta kz is less than 1. So using that approximation and giving back into the equation 13 and a few more equations like ks minus kt equals to delta kz back into equation 13, we can get the following equation, equation 14, which includes the amplitude of transmitted wave perpendicular and in terms of amplitude perpendicular of reflected wave. So AT perpendicular omega s equals to AT perpendicular omega s plus omega by c square p perpendicular I z upon 2 epsilon naught kt omega s, which can be further resolved into uh, the equation you can see here. So now the interesting part comes. Are we only interested in the order of the magnitude of AR perpendicular? So we can go back to equation 12 and we can see that AR perpendicular is equals to minus AP perpendicular upon epsilon naught root uh, epsilon t omega s omega t and all these things. But to only just we need to find order. So we can see epsilon t, epsilon r, and epsilon s. Both are the order of e ki power epsilon ki power half, and cos are the order of 1. So we can say like e power half, epsilon power half plus epsilon power equals to 2 epsilon power half. And similarly for this part, so 2 epsilon power half into 2 epsilon power half equals to 4 epsilon. So A R perpendicular is equals to minus P perpendicular upon E naught into 4 pi epsilon half uh, 4 pi epsilon, sorry. So here we have written that and we are putting back into the equation number 14. So we get our desired amplitude, which is amplitude of transmitted wave perpendicular, which is equals to minus pi p perpendicular upon 4 pi epsilon 1 minus 2 I kt omega z. So now the surface terms make contribution comparable to bulk term of thickness t. So we can find thickness in this. Uh, as you can see, kz is very small. So we can again reverse approximate this into exponential e raised to power minus 2 I k t z. And as we all know, the decaying constant of EM wave into a material is equals to amplitude at a function of r equals to a naught into 10 to the power minus uh, r by t, where the t is a decay constant or thickness constant of a material. So here we can see 1 by t equals to 2 kt, and we can write k as 2 pi by lambda. So we can write the thickness term to t equals to lambda by 4 pi. So So after that thickness, this 8T amplitude, as you can see, putting back into this and Z greater than T is going to 0. So as you can see, after that thickness, the wave is not propagating. This part is like, so now we can see the centrosomatic media. This part is little incorrect. Uh, so centrosomatic media, a Carto effective is only for the thickness of order of bore uh, bore radius, which is a naught, because uh, effect is only happening at surface, and so we get AT perpendicular centrosymmetric equals to 4 pi a naught by lambda into 8T perpendicular of non-centrosymmetric, which is approximately order of 10 to the power minus 3. So this is our end result, but I think this can be better understood. We just need to little bit search more. Uh, Hopefully, we can get back to this in the presentation. So here we have done some plots. Uh, as you can see, we have imported files, and here I have defined uh, uh, epsilon r omega. Epsilon r is in the air which we are taking. So this is returning 1. And epsilon t, we are using gallium arsenide as the material, so it is returning 12.35. And we are defining chi2 as a function of omega frequency and z, of course. Uh, and since the chi2 is acting within the range of thickness t, so for less than t, chi2 is 150 pico, which is for gallium arsenide, and for greater than t, it is exponentially decaying to 0. So this function is returning pi. And another way of defining function e uh, z is direction of propagation, amplitude, frequency, incident, and angle which is incidenting. Again, omega s equals to 2 omega i, which is again explained by my previous fellows. Epsilon of reflected equals to again function of omega I, and again epsilon transmitted is also function of omega s actually, and chi2 is again function of omega I and the direction of propagation, which is again defining within the function definition. Again, c equals to 3 into 10 cube power 8 meter per second, epsilon naught equals to 8.85 into 10 to the power minus 12, and mu naught equals to 4 pi into 10 to the power minus 7, all standard stuff. Again, we are using some basic things, defining k, uh, k equals to epsilon power half into omega by c. So for incident wave vector, uh, epsilon is of air and the frequency of incident wave. For reflected wave, omega is of again of air, omega epsilon r, and frequency of second harmonic generation, which is omega s. And for transmitted, the epsilon is of the material and omega is of second harmonic. And in terms of magnitude, omega s equals to 2 omega kt. But in the vector form, delta k equals to delta k minus delta k equals to ks minus kt, which can be shown in figure. This is ks, this is kt, and which is the delta k is in the direct z direction. And epsilon s is again kc upon omega s cos square. Now here we are defining, try to define uh, angle of reflected, transmitted, and second harmonics in terms of incidented wave. So going back to the Snell's law, and in this equation, you can see epsilon r half omega I sine I equals to all this following. So I have just taken the permittivity uh, under this and just taken sine inverse. So I've written theta r equals to theta I and theta t equals to sine inverse all this following equation, and similar for theta s, and defining p, which is polarization, which is epsilon naught into chi into a square, and defining p perpendicular equals to p. Since we are taking only considering in the z direction, so p perpendicular is equal to p. We have defined T1, T2, T3 just for convenience in writing amplitude perpendicular respective way and electric field for the same. So we have defined this function and we have also defined amplitude of transmitted and electric field of the transmitted, which is returning this. So we have tried to plot all this. So in the graph, as this is the propagation direction, the y-axis is the electric field, and we are showing the real values. As you can see, the green part explains the green and to this part within which is significantly large than the other part. It shows that the second harmonic wave is generated within the region, and it is also a very significant amount. Due to that scale, it is not showing the waveform, but it is a waveform. And after the thickness, the wave is dying out since the accessibility is going to zero, and similar for the reflected. Uh, And here we have tried to plot the uh, amplitude of all of this. And as you can see, the amplitude is constant till the thickness and it is gradually dying out. After the thickness, it is going to zero. So now I have done same thing for the non-centrosymmetric part. For this non-centrosymmetric part, you just need to change. You don't need to range within the thickness. Just chi is equals to for all the material, and we are returning same physics, same equations, and it is giving me that uh, starting with quadratic, but eventually going to a linear growth, which is due to reason of one root of 1 plus x square, which will become linear after a significant amount of propagation. And this is very natural. So we need to consider about the ratio. So the ratio of this, we have taken the ratio from the edge, uh, from the point where the waves start dying out. So I have put these values and it is showing 10 to the power minus 3, which is true, but I feel this part can be more explained and more worked on. So we will try to cover more in the presentation. Thank you guys. Was our presentation. We want to uh, mention all the references we have taken from Boyd, a few papers, and some more papers for the images and some values. And our contribution are Earth, Devansh, myself, Gargi, Gold, Mukesh, Praveen, and Ravi. For some reasons, Ravi was not here. So thank you everyone for staying till here. Uh, we hope uh, we hope to see you all in presentation. Thank you.